So in this video, I'm going to show you how to create counterexamples in the language of monadic predicate logic. Basically, a counterexample is an interpretation or a situation that shows that the premises is true while the conclusion is false, and thus it shows that the argument is invalid. So what we're going to do is go over how to do that step by step. So here we have this argument. This argument says that there exists an x such that the x is f if and only if x is g. Here, for the conclusion, it says that some x, right, there exists one x such that x is f or x is g. So what I'm going to do is first create a matrix representation. And what a matrix representation is basically the visual representation of the interpretation. So visually, it's a little bit easier to do first, and so we'll do that. So to begin, first you count out the number of different predicates that you have. Here we only have f and g, so that's 2. And we're going to write that horizontally on the rows. And then what we're going to do is create a matrix and add the first object, alpha, on the vertical side, and create a situation where alpha does not have any of the qualities that we've just listed. And so if alpha is neither f nor g, what that does is it creates a situation where the conclusion is false, right? Here the conclusion says something is f or g. Well, nothing matches that description, and so that's false. Here it says there's at least one object, right? One object being alpha, that it's f if and only if it's g. Well, apparently, if the biconditional has truth values on either side that match, right? False, biconditional false creates a true value. And so this would create a true premise. And so since we just said that our conclusion is false and now our premise is true, that creates a counterexample that shows that the argument is invalid. And so here we didn't have to do much. So if you start simply and start to calculate your truth values, you may end up with a very simple answer. So now we write the interpretation. The interpretation is different from the matrix representation in that the interpretation is in a list form. So here we say that the universe of discourse, right, consists of one object. And here the curly brackets will show that this is a set of objects, and the set of object is just one object that we have, which is alpha. And so the extension, right, we write that as ext of f. And the extension is basically the list of things that will have the quality f. And so here, since nothing has the quality f, we leave the set empty by writing the 0 with a dash through it. Likewise with the extension of g, since nothing has the quality g, that set is empty. And so this is our interpretation. We have only one object in our situation, and that object is not in the extension of f, nor is it in the extension of g. So this creates the counterexample to this argument form. Okay, so that was pretty easy. I'll show you right now why it is the case that, in more detail rather, why it is that this is true and this is false. Remember that we understand our quantifiers as consisting of all of the substitution instances. And a substitution instance is basically a particular instance within the variable. So here, since the variable is x, we can understand the variable as ranging over all of its objects. For the existential quantifier, we understand the existential quantifier as a string of disjunctions. And so here, the existential quantifier doesn't have a string because it's just one object, and so this is only talking about alpha. And since it's only talking about alpha, there's only one substitution instance. And so actually I'll write this over here. And so the substitution instance is alpha is F or alpha is G. Alpha is neither F nor is it G, so that creates a, I'm sorry, that's supposed to be false. False truth value for the conclusion. So, right, then our premise is understood since it's only got one object as a single instance. A is F if and only if A is G. And so because A is neither F nor is it G, we have two false values there, which makes the biconditional true. So, so that's why this is a counterexample to the argument. Okay, so let's look at a different argument. So in this one, what we'll have is not everything is F. That is, it's not the case that for all X, X is F. This does not semantically entail that for all X, it's not the case that X is F. That is, everything is not F. So here, we're going to do the same thing. We're going to start out by listing out all of the predicates, and since there's only one, that's pretty straightforward. And then we're going to list out, or begin by adding objects. Begin simply by adding one object and keeping it negative. So here, this says everything is not F, which means this is true, right? Everything is not F. And so to make this false, this object, since we only have one object, it's going to be all of our objects. Now all of our objects are F, and so that would make this false. But if we look at this, this says everything is F, right? If we take away the negation. So if everything is F, which it is, this is true, the negation would say that, would flip the truth value. So this would be false. So what we have is a false premise and a false conclusion, and that's not what we want. We can't change this back, or else what we'll have is, again, the values would flip. This is because since we only have one object, these two look very, very similar. However, if we add a second object, if we add beta, right, things would change. Now this quantified sentence is referring to both objects. It's saying both alpha and beta are not F, right? And so to break that down and to understand that, we can do so with its substitution instances. And so here, since it's a universal, we take out the universal quantifier and substitute the variable for the constants. So not F, A, right, is the first instance. And then the second instance is not F, B. So this says that both our objects, or rather all of our objects, are not F. Since alpha is F, then this becomes false. Since beta is not F, this becomes true. But putting those two negations together, you have a false conjunction. So that's all set. So here, for our premise, we understand this as a negation. So this is a negated quantified sentence. Our quantified sentence says everything is F. This says not everything is F. So because the negation is the main connective, we have to keep it as the main connective for when we try to understand or analyze the quantified sentence. Here, the negation must remain on the outside of the parentheses, and on the inside of it, we understand everything is F as alpha is F and beta is F. Right? Since alpha is F, this would be true, but beta is not F, this would be false, that gives us a false conclusion. Our false conclusion, right, if negated, gives us a true negation. So here, because of the false conjunction, for which we understand the quantified sentence is false, the negation creates a true truth value. So our premise is true and our conclusion is false. So we've just created a counterexample that shows that this argument is invalid. Okay, now we can write out the interpretation, and the interpretation is that the universe of discourse has two objects in it, alpha and beta, right? And the extension, since there's only one predicate, there's only one extension of f, only contains one object, and that object is alpha. And so here's our interpretation. Here's the matrix representation of that, which shows that our premises are true and our conclusion is false. Therefore, this argument is invalid. Okay, hope that was helpful. I'll do another video on embedded quantifiers or multiple quantifiers in a little bit.